silicon is at the atomic limit. The next material must be different. That different material is carbon, but not in its familiar forms. Diamond, graphite, graphene, and nanotubes are all pure carbon, yet each is completely different from the others. The key to this difference lies in a single p orbital per carbon atom, which creates a delocalized two-dimensional electron highway. That electron highway is graphene, one atom thick, stronger than diamond, more conductive than copper, and transparent. And if you roll that graphene sheet into a seamless cylinder just one atom thick, you create a carbon nanotube. The direction in which you roll it determines everything. It alone decides whether the nanotube conducts like a metal or a semiconductor. Whichever direction it takes, the resulting nanotube has a tensile strength of 150 gigapascals, while steel manages just 0.4. Not only that, but carbon nanotubes conduct heat 15 times better than copper. To make them, we grow nanotubes from catalyst nanoparticles in hot hydrocarbon gas, where they assemble atom by atom. But there's a manufacturing trade-off. Exfoliation gives perfect graphene sheets, CVD gives industrial scale, but no single method gives both at once. A related structure forms when exactly 60 carbon atoms close into a perfect hollow sphere that's a fullerene, another carbon wonder. Yet graphene's strangest property is that its electrons move as if they have no mass, traveling at 1/300th the speed of light. That massless behavior leads to quantum Hall edge states that are topologically protected. No defect can scatter them. Still, for all their perfection, we cannot yet reliably control whether a given nanotube ends up metallic or semiconducting. This matters because in every performance metric, nanotube transistors already beat silicon except for manufacturing yield. And a single nanotube represents the smallest possible transistor channel. It cannot be shrunk any further, physically. That potential was proven in 2013 when Stanford researchers demonstrated the first working carbon nanotube computer. But not every carbon nanomaterial makes a good transistor. Graphene itself lacks a band gap and cannot fully turn off. That's where other atom-thin materials come in. MOS is just 3 atoms thick and already possesses a direct band gap, ideal for switching. We can also improve graphene by placing it on atomically flat boron nitride, which boosts its electron mobility 50 times. Remarkably, if you rotate 2 graphene layers to a precise magic angle, the whole system superconducts and it's fully tunable with a simple gate voltage. Beyond electronics, graphene's transparency and conductivity make it an ideal replacement for indium tin oxide in flexible screens. In structural applications, mixing nanotubes into composites makes panels 50% stronger than today's best carbon fiber. And in energy storage, graphene anodes can hold 3 times more lithium than graphite, potentially tripling battery energy density. In medicine, those same nanotubes can ferry drugs to specific cells and release their cargo only when triggered by a change in pH. Their strength is so extreme that, in theory, only nanotubes possess the tensile properties needed for a space elevator tether. As sensors, graphene reaches the ultimate limit. It can detect single molecules. No man-made sensor is more sensitive. To quantify that strength further, a single flawless nanotube is 800 times stronger than high-strength steel. Yet 3 stubborn problems still prevent nanotube transistors from scaling: chirality control, precise placement, and overall yield. But progress is tangible. Designed molecular catalysts now achieve up to 90% selectivity for a single chirality. So nanotubes are directly competing with a silicon technology that physics won't let shrink any further. At the same time, graphene's mechanical flexibility is unmatched. It bends up to 25% strain, while Ito cracks at just 1%. In fiber form, nanotubes already outperform carbon fiber in tensile strength, though only at research scale. On aircraft, a graphene coating can conduct lightning strikes and spread heat, all while adding near zero weight. So nanotubes aren't lagging behind silicon, they are waiting for silicon to hit its final immutable limit. Meanwhile, the whole family of two-dimensional materials has expanded, now covering every possible band gap from 0 to 6 electron volts. Inside a metallic nanotube, electrons encounter zero scattering, its ballistic transport, perfectly lossless. Some of this has already left the lab. Graphene thermal interface materials are commercially deployed right now. And nanotube fiber strength is doubling every 5 years, steadily approaching the threshold needed for a space elevator. But there's a catch. A single atomic defect in an otherwise perfect nanotube can reduce its strength by 70%. Life itself chose carbon's tetrahedral form to build biology. Technology is now choosing carbon's hexagonal form to build the future. Same element, different atomic arrangement, entirely new physics. The transition from silicon to carbon has already begun. Carbon nanomaterials are no longer curiosities, they are commercial, and the roadmap is accelerating fast. The evidence: Intel, Samsung, and TSMC all have active carbon nanotube programs, preparing for the post-silicon era. The transistor launched the silicon age. Carbon nanotubes may now launch the next computing age. So which application of graphene or nanotubes excites you most? Tell me in the comments below. The era of full carbon electronics is projected to arrive by 2035. To put that in perspective, today's silicon transistor is 8 atoms wide, while a nanotube is just 10 carbons in circumference. The smaller one wins. If this changed how you see materials and computing, subscribe to NexaVision every Wednesday. If carbon changed how you see computing's future, hit the like button, it truly helps. Next on NexaVision, graphene-inspired biomaterials harvested from the deep ocean. Thank you for going inside carbon nanotubes. The future is built one atom at a time.